Hello. Tala, try and think about this question. Okay, so try and think whether this statement is true or false. I think if the statement is true or false, while we waiting for the rest. Discuss with your friend. Okay, any idea? True or false? Huh? Johnson. True or false? False. Why? Assume you mean you slice your group into 3 partition and then okay, so could it be could it be a coset of another subgroup or not? Sorry, what do you mean? I mean, could it be a coset of another subgroup or not? You get what I mean? Maybe the coset come from the other subgroup. So your argument was Q1H and union Q2H will have more element than H, right? What if this is a coset of another subgroup? You get what I mean? Is it possible? Why? I mean, just coset, right? Not every coset need identity, right? So what's wrong with not having an identity? I mean, if you want to prove it false, can you give a counter example? How about look at this one? H being the subgroup generated by 1, 2, okay, in S string. And what is H union 1, 2, 3, H? What are the elements inside here? Right? 1, 3, yeah. Is it 1, 3? Is 1, 3 here? 1, 2, 3 times 1, 2 is what? Oh, 1, 3. Okay, good. Anything else? Identity. Then 1, 2. And then hmm? Any more? 1, 2, 3. So there are 4 elements here. Okay, but there are 4 elements here. But S3 is containing how many elements? 6. So 4 doesn't divide 6, meaning what? It cannot come from it cannot be a cardinality of a subgroup. Okay. Branch theorem. There's no subgroup S3 that can define the union as a coset. Understand? Any question? Question? Okay. So the problem here is the cardinality of coset might not divide the cardinality of the union might not divide your group cardinality, then you won't have a subgroup that has the same cardinality. Okay, so it cannot come from a coset. It cannot form a coset. Okay. So the next question is, when is the union of two coset a coset? Can you give a criteria? When can a union of a coset be a coset? So the next question was, when is the union of two coset a coset? Can it possibly be a coset? If can you give a criteria? Okay. So my claim is yes, you go back and check. So my claim is when there is a G in G such that G of the union of the coset is a subgroup G. Okay, this is my claim. Maybe you can find the other criteria. Okay, but this is one of the answer. You can try and prove it. So one example was H. If you take 1, 2 again, but this time I look at it as a subgroup of X4. Then we can see that H union the coset 3, 4 times H is a subgroup in G. You know this subgroup, right? H union 3, 4 times H. You know this subgroup here? The Klein 4 group. The kernel of the homomorphism from S4 to S3. Do you remember the subgroup, order 4 subgroup? Identity 1, 2, 3, 4, and 1, 2, 3, 4. 1, 2 disjoint union 3, 4. Yeah, that's subgroup. H union 3, 4, H. Okay, try and check. I try and check this thing here. Is it true? Okay. Yeah. Very good exercise, huh? Try and do this exercise. Okay, maybe you can give other criteria. Maybe better than mine. You can try out. Okay, any questions so far? I have update the letters typeset note, and then all the lecture note I also compile before midterm, so you can use those for revision. Okay, and I think Arting solution is quite complete now. We have a previous solution and also solution done by Tang Ping and Hong Rui. Yeah, I think it's quite complete until 2.8 now. So you can try them, or if you don't try them, at least read them and see what concept is important. Okay or not? Any question you want to ask about exam or not? 啊，做什么？什么是做什么？出什么？嗯，出什么？很难讲诶。But one hint is maybe there's some question from the textbook. Which textbook? Athena? So make sure you do those questions. Which question? You will know when you are on. So make sure you do. For sure, there's some question from there. There exists. There exists. Okay, there exists. Okay. We still meet tomorrow. So if you still have question tomorrow, can ask. Okay, make sure you ask. When's the exam? Thursday. What time? 5 to 7. Where's the venue? Where's the venue? Which classroom? 哪个课室？不是也来不要去错课室没有人在那边哪个课室？Where's the classroom? Check make sure you check the announcement Yeah, so it's the next door. Okay, F4G1. Okay, make sure you come to F4, not A1. Right. So last time we mentioned about Zn, right? Zn, there are two ways to see Zn. When you learn Zn, it is just a remainder. I don't know. You learn by using remainder. Okay. But in this class, I taught you using equivalent class, right? Okay, so today we're gonna see the difference between these two. Okay, what's the subtlety between these two? Okay, how subtle is the difference between these two? So let's start with Z. Okay, the integer. Okay, the well-known integer. And you form a surjective map. Okay, to this so-called Z3. Right, so-called Z3 here. This Z3 is what? Basically just 0, 1, 2. Okay, very honest 0, 1, 2. You know what it means by honest? 诚实，数学家很喜欢诚实这个特性 ，honest 所以不要骗数学家，因为你也骗不了。Okay, so honest 1, 2, 3 here. Okay, so what's this map here? This map is called MAT211. Okay, do you know what this map do? For example, I give you a number, let's say 7. 7 should go to where? Let me check one of the person. Hey, Menchun 在哪里？Menchun 没有来了，赵瑞来了，Menchun 就没有来。怎么讲？轮流那就问赵瑞了。来，赵瑞 ，7 mod 3 is what? Well, 7 mod 3 is 1. How do you compute 7 mod 3? Okay, so you divide 7 by 6 and then you see what's the remainder. Okay, so you can see that the remainder of 7 is 1. What number also have remainder 1? Sorry? 10. Good. 10 also have remainder 1. So you can see that this map is actually not what? Not injective. Because two different numbers get sent to the same number 1. Not injective. Okay. Can you quickly see why is it surjective? Can see why is it surjective or not? What's the pre-mesh of 0? 3n. So multiple of 3. How about pre-mesh of 2? 3n plus 2. Okay, so there are infinitely many of pre-mesh there. All right. Also, at the same time, last week, what did we say? We can send Z. Use the other arrow. We can send Z to this quotient, so-called quotient group. Okay, we prove that it's a quotient group. So how do we prove it? How to form quotient group? The subgroup must be what? Normal. I guess the subgroup must be normal. But in our case here, Z is abelian. So any subgroup should be normal. Okay. So you form this quotient group. What's the element of quotient group? Crossing. What's the element here? How does this set looks like? What's the element inside here? You know? It's a set of what? Sorry? Group? Yeah, so this group is set of what? What's the element inside here? Whenever we talk about set, you need to know what does the element. So what are the elements inside a quotient group? You know? Coset, right? Okay, so these are the coset. How many coset here? What are the coset here? 3z, and then 1 plus 3z, and then what? 2 plus 3z. Got 3 plus 3z or not? Why? Why not? What is 3 plus 3z then? 3 plus 3z is just 3z. Okay? 3 plus 3z is just 3z here. So what are these coset? These are the coset that partition z by the subgroup here. So what's this map here? What do we call this map? We call it pi last time. Okay, so there's a pi here. And then we prove that this pi is surjective. How do we construct this pi map here? You can think of it as a projection. Okay, it's a projection. So you project x to where? You still remember? Project x to where? Last time the theorem says send A to AH. Okay, so in this case here, you send to where? Send to the x plus 3z. Meaning what? You send to the coset that contains x. Okay, you send to the coset that contains x. But if you map x across, what is this map here? This is x mod 3. Okay. So the claim here is we can complete this triangle. Okay, we can complete this triangle. And this triangle, how to complete it? So actually, there's a map from the quotient group to the codomain of the surjective. So there's a map from Z mod 3Z to Z3. Okay. But how to get this map? What do you think? What can we do here? What do you think? What do you think? What can we do here? So this is a map between what? I give you a coset. You need to give me an element in the codomain. How to give? What do you think? So I mean, you can simply do, but what we want to do is we want this diagram to commute. And what do I mean by the diagram to commute? So you should see that there are two ways, okay, to go from the starting point to the end point here. Can you see there's two ways? Okay, one way is the horizontal map. The second way is going down. Okay, going down and up again. So to make this diagram commute, there's really only one way you can do it. Okay, which is just send s plus 3z to s mod 3. But you can see that when we do this definition, you are picking the representative. So there's something to check here. You need to check whether it is well defined or not. Moreover, if you define like this, actually this map is a isomorphism. Okay, actually it is a isomorphism. So this is what we're gonna prove tonight. Does it make sense? Can you see the isomorphism here? You can see or not? So if I write down the isomorphism here, you really see was, oh, here is a coset product. And then on the other side, we'll have a Z3 plus. Okay, oh, that's just, yeah, plus. So we send 0 bar to 0, 1 bar to 1, and then 2 bar to 2, actually. And so this is the isomorphism that I will be mentioning just now. Okay, so we're going to prove it in general. Why is it true? Any questions so far about this example here? Any question? Okay, is it clear? What we're going to do? Yeah. So this one, I will say that exists. Let me go deep. Okay, 繁星有问题吗？繁星，在想什么？分享一下，想什么？因为我也很压抑，现在对吗？啊，是什么啊？什么意思？OK，isomorphism 什么意思？看屏，听得懂吗？听不懂不用紧，我们还可以再解。Adjective homomorphism 知道什么意思吗？要检查两个东西嘛，projection 跟homomorphism。所以是 is a group homomorphism. Is a group of map, right? Because on the coset, on the quotient group, you have group structure. On Z3, you also have group structure. Okay, so this map actually preserves group structure. And then it's a bijection. That's subjective. 对不对吧？以前呢？以前，对不对？看你的眉头都要很深，有问题吗？没问题。Okay. Okay. So let's prove it in general. So this is a first very important, very strong result in algebra. So please listen carefully. So this is called the first isomorphism theorem. Okay. 没有学会这个啊，你不可以毕业。OK 吗？大家如果有问题就尽量问，尽量问，尽量暂停我也可以。So first, let phi be a surjective homomorphism. Okay, so it's a surjective homomorphism with a kernel n. Okay, with kernel n. Then the quotient group, which last time we denote as G bar, which is simply G mod n, is isomorphic, okay, to the image of G, if we have 5, which is G prime. Right, this is what we're gonna prove. But it's not, need too many. And how to get this isomorphism here? So let pi be the projection map, or in the textbook you will see that it is called a canonical map. 大家知道什么叫 canonical 吗？有人知道吗？所以英文比较好，对不对？canonical 是吧 真东西，no，设定这个是这个形容词是什么意思？canonical 不是 con，是 canonical，canon 啊，no 啦，canon 不懂，没有，不懂，canonical 啊，有人知道吗？canonical 是什么？原本啊，很靠近原本，就是应该做的标准，可以也是讲标准吧。啊，典型还蛮靠近啊，典型蛮靠近，就是你看到这个东西，你会做的一样事情。canonical. When you see it, you will define it this way. Okay, so let's write down the canonical map later again, and then we try and argue why is it canonical. And then the claim is there exists a isomorphism phi bar from G bar to G prime, such that the phi here is equals to phi bar composed with pi. Okay, so you see a lot of algebra here. So don't worry, you should draw it out. Okay, so draw it out one by one. Draw from first line. Okay, first line says what? There is there's a map from G to G prime. Okay, using this phi here. And then what object you have? You have G bar. G bar is G mod and the quotient group that we defined last time, which is what? Set of left coset. Set of left coset. So let pi be the canonical map here. So what's this map doing here? It sends every element in G to what? To the coset that containing this x. Okay. Is it clear that why this xn contain x? Is it clear? Why this is a coset that contains x? Why xn contain x? 成 B，这叫成 B 吗？Okay. Why xn contain x? Why this coset contain x? 自己是自己的培基。喂，这句话不对，因为它是 element，培基是个 set，所以他们不能够。Sorry，那我的问题是为什么？Why does xn contain x? So my claim is I send x to the coset that contain x, right? So why xn contain x? Why the coset Sn contain x? Why? Sorry? Why? You need help? No. Why? I mean, why? You haven't answered my question yet. So n has an identity because n is a subgroup. So in particular, x times e is inside xn. Okay, so I'm sending x to the coset that contains x. So this is what they call the canonical mapping. Okay, so it's kind of canonical, right? Usually, you only go to your own house, right? You won't go to people's house, right? Is it correct? You will. Hey, dangerous, this guy dangerous. He will go to other person's house. Not canonical, this guy. Dangerous, Okay. Right. Okay. Good. So now the claim is there exists a isomorphism here, which is phi bar. Okay, later we'll define this. Okay, and it's a unique isomorphism. How about the last equality here? What does this last equality here? Where is phi? Phi is going from G to G prime. What is pi? Pi is going from G to G mod n. And then P bar, P bar go from G mod n back to G prime. So they both have the same domain and codomain. So we want them to be. Okay, we want them to. So when they're equal, this is what we call this triangle will commute. Okay, this triangle commute. And because you go from two ways, they're equal. Does it make sense? Okay. So this x element here can either go to G prime first, or it can go to its coset first and then back to G prime. Okay, and then they have to be equal. And then we will say that they commute. So in this case here, there's a terminology here. So notation here or terminology. In this case, we will say that phi factors, okay, factors through pi. Okay, phi factors through pi. So y factors through pi, you can think like it's a number like 4 equal to 2 times 2. 2 is a factor of 4, right? So now you split phi into 2 homomorphisms. Okay, you split phi into 2 homomorphisms. So you can split the surjective map into 2 homomorphisms. So factors through pi. Okay, no? Okay, we don't really mention phi bar here. Why? Because this phi bar is kind of get determined by your pi already. Okay, because later we'll prove the uniqueness here, existent uniqueness. So actually, it is like come in a package. Okay, it comes in a package. This phi bar, and once you have this pi here, it will come in a package. Okay. Factors through pi. Yeah. So you break phi into 2 parts. Okay, good. So the first thing we do is to find this phi first. Okay, we will try to find this phi. Sorry, phi bar. Phi is given. I will try to find phi bar. Okay, so in particular, we work on this one first. Okay, let's find how do we do it. So let's prove. So let's define. So we first define phi bar from G bar to G prime. Okay. So what do you think you should do? What's the sensible thing that you need to do here? What do you think? Where should you send this coset to? Do you think? Actually, you cannot think randomly because question already tell you what this phi bar should behave. Okay, so look at this. Look at this equation here. What does this equation tells you if you apply on an element x? How should you define phi x bar? What is pi x? Sense x to x coset. Okay, meaning this is x bar. So you see, this property already tells you how to define it. Okay, if you define this way, then this commutativity will hold. Okay. So, meaning what? I need to send phi bar to where? Can you see where is it? I need to send phi bar to where? That's me. Sorry, I need to send x bar to where? Sorry? Phi x. Okay, so I need to send it to phi x. Okay. So meaning, how do I send the left coset? I look at what's the representative, and then I just see how phi n on x representative. Okay, but you see, Camping asked me, when do you need to check well-definers? Okay, when do you want to check well-definers? So look at here. This definition is defined on equivalent class. But when you define it, you just use representative. So meaning what? if you have different representative, will they go to the same thing or not? Okay, so let me write out what I meant here. Not that. Phi bar is well defined. Why? So let's check it. Suppose we have x bar equals to y bar. Okay. Then what? This implies what? This implies that the coset, both coset are the same. But what? What's the TFAE proposition tells you? X is in Yn. Any other useful one? I think the other is more useful. X inverse Y is in where? N. Okay. But N in this case here is a kernel of your homomorphism. Meaning what? P of X inverse Y is identity. So you can use homomorphism to split all the terms out so that you will get Px equals to Py. Okay or not? So if you start with the same equivalent class but different representative, you still get the same image. Okay. If you start with same equivalent class but different representative, you still get the same image. So this is well-defined. So remember, well-defined definition is what? It's the opposite, it's the converse of the injectivity. Okay, if you have the same thing, you should go to the same place. Okay. Injectivity is what? If you go to the same place, you should come from the same thing. Okay, so it's well defined. What else we need to check? So a few things we need to check, right? So at least 3 things we need to check here. So 3 things to check. Check that phi bar is an isomorphism. Second, phi bar satisfy the commutativity relation, which is phi equals to phi bar compose pi. Okay. So this one we checked already, right? This is by construction. Okay, just now we checked already. Okay, this is true by construction. And what else? We said that this map is unique. Okay, so there are 2 more things to check here. Isomorphism and unique. So just now we said that to check isomorphism, we need to check homomorphism and adjective. Okay, so there are 3 more things, 3 small things. So for homomorphism, okay, for homomorphism, how to check? Okay. So phi bar is a homomorphism. Meaning what? You take phi bar of x bar, y bar. Okay. What is x bar, y bar here? If you don't like x bar, y bar, you can write it as x n, y n. Then what can you do here? Huh? Sorry? Take what? And what do you do to n? Sorry? Take it out? How do you take it out? Take from where? Remove n? Factor? What do you mean? How do you factor n? Seng said commute. Which one can commute? Ny can commute to y and y. Why? n is normal. Okay, n is normal. Okay, so in this case here, by definition, where do you send xyn? By definition, you send xyn to where? To phi of xy. But phi of xy is a group homomorphism. So you can split them. But by definition again, you will get phi bar xn times phi bar yn. Okay. So phi bar really behave as a group homomorphism. Okay. Right. How about part B? Let's show that phi bar is injective. Okay, like how to check phi bar is injective? How do you start? How do you start injectivity proof? Hi, Eugene. How do you start injectivity proof? Suppose what? Hey, on the proof 1 to 1, you suppose 1 to 1. What is equal? Phi bar x bar equals to y bar y bar. Okay, so you want to deduce that x bar equals to y bar here. 好像很熟悉耶，刚才就做过这样的东西了，不是？有吗？有做过吗？ If you have this, this implies what? Sn. Hey, wait, sorry, too fast. So this implies what? Phi x equals to phi y, which implies what? X inverse of y is in the kernel, which implies what? The left coset of x containing x is equal to the left coset containing y. Why? Because the TFAE is equivalent, so you can go back, forward, go back and forth. Okay. So we use the other direction for injectivity. Very nice, oh? Is it very nice? Injectivity and well-defined just come from the same proposition. Okay, come from the same proposition. Okay, C. Lastly, you need to show that, moreover, you need to show that phi bar is surjective. 我写错什么东西啊？啊？哦，sorry, and thank you. So surjectivity, what do you need to do? 来延伸 what do you need to show surjectivity? For everyone. For everyone. So phi bar, okay, 提醒你一下，这个 phi bar going from where to where? Where's the domain? Where's the codomain? Going from G mod n to G prime. Okay, 我给你全部 space 了，告诉我什么是 surjectivity 的 definition. For every 什么 For every phi bar? Okay. Why and where? Good. What do we need to find? Want to find, what do you call that? Z bar. What's that? Z bar equals to y. Why you have the same choice as mine? Huh? Okay. Okay, good. So how do we find this Z bar? Oh, 有点歪楼啊你们。How to find this Z bar? Z bar. Sorry? 什么 How to find this Z bar? Hmm? How to find? Find this Z bar. Well, you can do some working here. What's 5 bar Z bar be? By definition is what? 5 of Z. 5 of Z. So you want this 5 of Z to equals Y. So what should this Z be? Can you find the Z or not? Can you find it? Find the Z that work. You know anything about this phi or not? There's only one condition on phi. Actually two. We know about the kernel and this phi should be surjective. So you have something from the whole domain, right? You have to find something the pre-image, right? So meaning what? By the surjectivity of phi, what can we find? There exists an x in G such that phi x is equals to y. Okay. So how do you set z bar here? You just take z bar to be x bar. Correct or not? Check. So we need to check. We need to check this. So that what? Phi bar of z bar is what? Equals to phi bar of x bar, which is by definition phi x. But how do we find this x? Exactly, it is equal to y. So we use the surjectivity of 5 only. Okay, because when we define this phi bar, we really use the map 5, actually. Okay, yeah. So, hence, this is the desired isomorphism. Okay, so the proof maybe sound quite routine, but this result is very shocking. Okay, this result is actually very shocking. Although this proof is like very elementary, homomorphism, isomorphism. Okay, but this result is actually shocking. Why is it shocking? What can you see here? G bar by its own right is a group, but G mod n here is also a group, but this group is special. This is a left coset. Okay, so you can see that the set of coset when they multiply is similar to another group structure. Does it make sense? Okay, so G bar here is just a normal elements, but G mod n here is a set of set. Correct or not? Set of coset. So it's a set of set. Okay, then this set can multiply together. Coset. Okay, so the result here is shocking, although the proof is quite elementary. Right. Lastly, let's show that it is unique. Okay, let's show that it's unique. So how to show it's unique? So how to show something is unique? How to show something is unique?是unique。什么证明是独特的这个东西啊？来，就有这个，怎样证明就有全世界就有这只吧？怎么证明？吃下你能不能再找另外一只出来？如果你找得到它不一样，这样它就不 unique 哦。但是如果你找另外一只出来，其实就是它，人它就是独一的了。Okay, so meaning what? Suppose there is another isomorphism. Okay, so suppose there is another isomorphism here. So suppose there is this another isomorphism. Okay, 叫什么名字？叫什么名字呢？ Psi. Psi. Okay, good. Psi bar maybe. Okay. Psi bar. Such that psi also commute. Psi bar. Psi bar. Okay. All right. So what can we do here? How to show psi bar is equal to phi bar? 很好笑。我觉得这边的频道跟那边频道在一样，每次一起上。 Okay, so what do we get here? So we can see that both these composition, right? They equal to true phi here. Okay. 这么。激动啊 Okay. So, what to do here? Can we play anything around here or not? Can we compose with pi inverse? 可以做 pi inverse 吗？可以咩？ Well, if we have pi inverse, it's easy, right? We just cancellation law. Why there's no pi inverse? Maybe not injective. Most probably is not injective. Okay, most probably is not injective. So there's no inverse. Right. Just ask me, right, how to show something is bijective. So one way is to show the function has an inverse. So left inverse, right inverse, you need to check. Or you do what I do just now, check injectivity and surjectivity. So then there may be no inverse here. What else can we do? Uh, I mean, we still can do something, but we cancel on the other side. Okay, let's see if this is any useful or not. So how about we cancel phi bar? Because obviously you can do this because we just show that phi bar is, hey, I swap. Wait, sorry, I confused myself. So I do what? Okay, I do about psi bar bar. Okay, we do psi bar. Okay, psi bar is an isomorphism. Okay, can we still deduce anything or not? So this bunch of thing is equals to pi. Is it possible? How is it possible? So on one side you have composition of three things and equal back to what you started with. Okay, when is this possible? 讲一下. We finish this proof with Algebra. Okay, 讲一下. Can we conclude that phi bar inverse compose phi bar, sorry, psi bar inverse compose phi bar is identical? Can we conclude it? Well, I mean, if pi is identity, then obviously that composition is identity. If pi is not identity, huh? Usually pi is not an identity. Usually pi is not identity. We will claim that actually this 5, this composition here should be identity. Okay? Only then these two sides were equal. Like sorry, compose. When we multiply function together is compose. Sorry, use as well. Sorry, use as well. 因为我看到我的电脑里面 Euler notation. Okay. Is it okay or not? You feel weird? Where's the circular reasoning? 肯定没有 circular 的话就有问题，肯定是没有的，所以哪里你觉得 circular？ If it's not identity means what? If it's not identity, um, if it's not identity, you should derive some contradiction. Because if it's not identity, then there's no identity, then there's no identity. Then you can derive. If it's not identity, it will still be an isomorphism. Okay? Because it is a composition of isomorphism. Think of it, right? Or not? If it's any idea. If not, just take it like this. It must be an identity, otherwise two sides won't equal. You get what I mean? So I mean you can write down the map, right? So well, let's look at what does this map doing. For example, right? This pi will send A to, let's say, AN. Okay, on the other side, A will also go to AN first. And then AN go where? You send AN to phi A. Okay, and then you send phi A to where? Okay, wait, let me think. What am I doing here? So I send it to phi inverse of phi A and then N. Okay, so we want what do we want? We want that P inverse phi A N equals to A M. Okay, we want these two to be equal. Okay, equal on the element wise. We want this to be equal. And then this has to be equal for OA. Okay, so this has to be equal for OA. OA. In G. So the claim is this, there's only identity with B. And the claim is there's only identity can do this. You won't give up. The claim is only identity with this. For OA. Well, I mean, you can check on one very elementary element, right? In N. Which one? For example, check E. Well, I mean, E should be easy because the isomorphism send E to E. So obviously it's satisfied. Anyway. Yeah, the claim is this composition is identity. Only identity can do. Sensing. Sensing. 还是觉得不够 rigorous？嗯，相信吗？Do you believe? Yeah. 嗯。And once we know that this composition is identity, obviously this will imply psi bar equals to 5. Yeah, working. Yeah. What do you mean? Psi, psi bar. Okay. Yeah. Uh, yeah. Yeah. Psi is an element Q, right? Yeah. Well, no, wait. So this sidebar, wait, let me think. This sidebar, wait, I mean, let me think. Oh, I think I'm not quite right. Because this sidebar, actually, I don't know what this sidebar doing. What I know this sidebar do was only isomorphism and such that the whole thing commute. So actually, it is not true that I write this. I can write this because I don't really know this how this phi get defined actually at this side. Okay, actually I don't know. What I know is I just know that this side is the isomorphism and there's a commuting relation there. Okay, so this is not true actually. So we really need to argue from here actually. Why is it a psi bar inverse and phi bar is psi? Hey, yes. Can you use the pi image of pi? Yeah. Yeah, because both of them must have the same result if the input is from image of pi. Sure. Their domain both are over. Yeah. They must be equivalent. Mhm. Yeah, sure. I mean, wait. No, I mean, you are just you just reciting this equality here. You're just reciting this equality. Yeah. Mhm. If I add one more restriction that image of pi is everything that is. So that means you must. Wait, so wait, let me try again. So you mean, so let's say phi send a to an, and then on the other side a to an also. But in the end, you know that it has to send to an also. This is what you mean, right? Because they have to equal on image. The input can only be an. Input. All the possible inputs are equal. What? All of the possible inputs for functions result the same concept. You mean you look at this three composition or just two? Three of them. Isn't it this is what you want? So on the right hand side, you send A to AN. On the left hand side, you also send A to AN first, and then you go through this composition, but image have to be the same. So this composition here will send AN to AN actually. And then the claim is the map that do this has to be identity. The map that do this should be identity. So I mean, where's this map going from? This composition here. Yeah, that's right here. So this composition is going from where to where? From G mod n to G mod n. Okay, from G mod n to G mod n. And then this is a map that sent AN to AN. We already checked through this by assumption. And then my claim is this map is actually the identity map. Sorry? 呀，洛星。万一是 permutation， 对，我们就是要 rule out 这些 possibility， 有可能是 permutation。Yeah， prime inverse 啊 ，prime inverse。Okay, yeah. So you mean you use right inverse probability? Is it correct or left inverse? So right inverse. So you go right to choosing and then you send it back. Oh, okay, yeah, correct. Okay. Well, okay, one way you can use the right inverse. And then the other way is to see that this map send AN to AN. This should be a identity map. Because you send every concept to itself. 对吧 ？identity map 是做这样的事情嘛，把自己送回给自己。Okay. Okay, so one way you can use right inverse, or you can use you check where it sends all the cosine using the equality. So you send every cosine to itself, n to n, an to an, bn to bn, cn to cn. So this is just identity map. So this is a map on cosine. It's not map on elements. Map on cosine. There's a map between set of set. Okay, or you can use what Rachel said, the right inverse exists. Okay, not inverse exists. No, there's a subtlety here, right inverse and inverse. So you only satisfy pi inverse is identity. Okay, so there's no pi inverse pi is identity. No, that one. Only on the right. Okay, right. So what I put here. So we're done here. So the corollary is corollary. So if we have a group homomorphism, okay, with a group, sorry, with what? Homo, with kernel, and what do we do? And because there's no surjectivity here, we call the image H prime. So it is a subgroup in G prime. Then the quotient group G mod n is isomorphic to H prime here. Okay, so this is the result of the corollary. And then this also answers the question that every normal subgroup is also a kernel of a homomorphism. What's the kernel of the homomorphism here? This is the canonical map. Okay, for every normal subgroup is a kernel of a canonical map. Okay, every subgroup, every normal subgroup is a kernel of a homomorphism map. So let's give some example here. For example, Z mod 3Z, okay, is isomorphic to 3-element set, okay, the one I told you just now. And this is isomorphic to the cyclic group of order 3. And you can bring out all our kernel example before. For example, GLR mod SLNR. Still remember what's the why SLN is a kernel under what homomorphism? The determinant homomorphism. Okay, determinant homomorphism from GLNR. Okay, so let's write down the map also. So here's mod 3. Here use determinant. And then you can see that this is isomorphic to the non-zero real number. Okay, so these require proof. I just give you example. These require proof. Every one of them require proof. And also xn over an. Okay. So what's this? This is the sign homomorphism. Right. Alternating group is an even permutation set. So this is isomorphic to what's the image here? The image here is just plus minus 1, which is isomorphic to a cyclic group of order 2. What else? R. If you quotient by the trivial group here, hey, does it work? 没有抄错东西啊。What's the homomorphism here? Let's check. Anyone remember there's a map from R to EX? I think, let me think first. So this map is the exponential map. Okay. And then we say that this X is injective, right? E to the X is injective. So injective, there's only one thing inside the kernel, which is 0. What else? So C cross quotient by the set of root of unity. Okay, set of root of unity, how do you express it? Let me think. Not just root of unity, actually the x one. Okay, how do you put x1 in the top? Okay, so this is also isomorphic to non-zero multiplicative real number. Okay, so what's this map? This is the modulus map. Okay, and then lastly, we have R to x1. Okay, so what's this map here? Oh, this is the e to the 2 pi I x, right? So what's the kernel here? So the kernel here is the integer number. Okay, so these are the isomorphism that we have. Okay, how to show this isomorphism? You need to test how to use the theorem. First, isomorphism theorem start with what? Let phi be a surjective homomorphism. So you need to give surjective homomorphism first. Okay, all of these are surjective homomorphism. Okay, and then how do you get the isomorphism result? You need to show that the thing that you quotient out is the kernel of your surjective homomorphism. And then by first isomorphism theorem, you can get this result. Because on the right hand side are all the images surject on this image. And so to show this isomorphism, 不要傻傻的去 prove isomorphism, prove homomorphism. You can use the first isomorphism theorem. Okay, so let me write down the strategy. So to use first isomorphism theorem, okay, fit. What do you do? Okay, find the surjective group homomorphism. Second, show that n is the kernel of, let's call it 5. 5, 3 by FIT, you will know that G mod N is isomorphic to the image of G. Okay, so this is a strategy to use FIT. Okay, no? Okay. Otherwise, you need to start whole story with the proof of build, map, and then tell me how to send code set, and then show surjective, injective. Also can directly do. Okay, if you want to use FIT, you just need to show surjective first, and then show kernel, and then use result. But if you want to show straight, what do you need to do? Prove surjective, injective. Okay, prove surjective, injective, homomorphism. So instead of showing injectivity, you just need to show what's the kernel is enough. Does it make sense? So you replace the injectivity property here by showing kernel. Okay, because we will prove in general. Why is it true? Okay. Any question? This is very strong result in mathematics, in abstract algebra. Actually, there are more. Since we said first, right? There's second and third. Okay, so there are second and third. We won't prove it, but I just state it here. So maybe show you a picture here. 对，我要下课了。要了，很快。因为看到差不多差一点，讲完它吧。每个都很重要，死了放不下。OK， 要完了，这个没有 proof，OK， 我要下课了，稍安勿躁，来。哎，有一个建议是说，我们上到8:45，然后提早下课，40分。你们怎样？就这个上完哈。但是你要上厕所就去吧，上厕所就去。OK， 40分啊 ，OK， 好，可以，还有17分钟，那我们就上到晚，因为这边很精彩，太精彩了，不想不跟你说，太精彩了，哎，很精彩，来，很精彩啊！下一个是 second 跟 third， 我们会拖的，我们。如果你们要上去厕所就去吧。然后 ，very important， 不是 important 啊 ，but very interesting result here. So there are second isomorphism and third isomorphism theorem. So what does second isomorphism do? If you have another normal subgroup, what you can do is you consider the product, Hn. Okay, and then quotient out by n. Okay. Wait on. Do we know that Hn is a group or not? Do we know it? Product of a subgroup not necessarily a group, right? Or is it a group here? Okay. If you took two elements inside Hn, which is what? H1 N1 and H2 N2, does it still live in? Why? Because N is normal. Okay, so it actually is a group. Okay, actually it's form a subgroup inside your G. What is it isomorphic to? It is isomorphic to H portion out by the intersection. H portion out by the intersection here. So meaning what? If you take product of Hn, right, you are not far from being H. You are not far from being H. Okay, you are not far from being H. Okay, and then quotient by what? Just quotient by the intersection. Okay, so how to prove this isomorphism? I just need to tell you what's the surjective map here. Okay, so the surjective map here is I use the other way around. Send H to Hn. Okay, go from right hand side to left hand side. And then you should prove that H intercept N is the kernel of this map. Then you are done. Okay, to show this isomorphism because you can use first isomorphism here. Second, can you see second or not? Look at second here. Does it look familiar? Familiar or not? Familiar? Familiar? Okay. This is like a number operation dividing. Okay, so it's like 2 over 3 equals to 2 over 5 divided 3 over 5. But here, remember, here are quotient group. Oh, what does it mean by quotient group here? G over K, set of coset. H over K, set of coset. So it is a quotient by a set of coset. Does it make sense or not? So the level here is set of coset. But here, set of coset over set of coset. You get set of coset. Set of coset. On the other side, you only have set of coset. So we go up level. Go up level. Okay. Okay. So you might wonder what's the surjective map here. Okay, so the surjective map here is sending GK to GH. So what's the kernel here? So the kernel of the map here should be H over K. So you can try to do it. Okay. Okay. So whenever you want to see this kind of show this kind of isomorphism, right? You should build a surjective map first. And then after you build the surjective map, look at does the kernel equal to the thing that you quotient by? If it equals, then you have this isomorphism by first isomorphism here. Okay. So the key here is whenever you want to show isomorphism between quotient group, what do? You build surjective group homomorphism and then check that whether the subgroup that you quotient by is the kernel of your group homomorphism. Okay, does it make sense? If it equals, then by first isomorphism theorem, you have this isomorphism. Okay. Right. Let's continue. I won't write because we won't examine on this, but I want to tell you the story here. So what's the application of quotient group here? We can decompose group. Last time I already showed you one way to decompose group, right? You can decompose a finitely generated abelian group into one product of cyclic group of order power of prime and z. Okay, multiple of z. Here is another way to do it. Actually, that proof need these tools to prove it. That's the theorem that I omit proof last time. Actually, you need this tool to help you to prove it. So once you have this tool, maybe you can try and prove what we had last time. So the first definition we gave is what is a simple group? Okay. So this simple group is like a prime in your number. What does prime do? It's a leading along more than that. You know prime number factorization? Okay, so all the number can be factorized into product of prime. Okay, so we are going to do the same thing with this simple group here. So a group is simple if it is non-trivial and has no proper non-trivial subgroup. Okay, non-trivial, non-proper trivial subgroup. So for example, what? Cyclic group of order prime order P. Okay, if you try and build subgroup, you will always go back to yourself. There's no non-trivial. You can try it. Why? Because every element in order P must have order dividing P. Meaning what? Either you are order 1 or you are either order P. So if you are order 1 is the identity. If you are order P, you should generate the whole group again. Okay, so there's no non-trivial subgroup here. The other one is the alternating group is also simple. Okay, this is simple for n greater or equal to 5. This fact, I think is quite hard to check. But this fact actually related to Galois theory. Okay, if you are interested in AA2. Actually, this is the result about not all polynomial equation of degree greater than 5 is solvable. Okay, you cannot solve using root radical. Okay, so there's some implication by this group theory here. Okay, because A is simple, so there's no non-trivial subgroups in there. So what's the main point here? So how to build our group here? So this is the Jordan-Holder theorem. Any group has a unique composition series up to isomorphism. So what is it doing here? So you can find a chain of normal subgroup, okay, inside your G. Where you can find a chain of normal subgroup inside G, where these where the quotient Hi plus 1 over Hi is simple. Okay, so meaning if you take consecutive quotient, right, they are simple. You write down this chain and then you take consecutive sequence, it is normal. And then this theorem proves that it is unique. Okay, so there's no other choice. Okay, so there are no other choice to do this. And here come the big result in finite simple group theory. So this is a classification of a finite simple group in this work. Okay, so basically there are cyclic group, as we know already, and alternating group we also know. Okay, because this is the kernel of the terminal homomorphism, and the other are quite peculiar. Okay, so for example, 3 you have what? Projective XLN. So what's projective XLN? So it's just not SLN, or there's some more other things inside there. And then last one is the most peculiar one. They cannot quite get them into some special type, so they just call it sporadic. Okay, and then the last one to find is, where is it, my monster? Yeah. Okay. There's one very big monster here. Okay, so monster group, there's one group called monster group, is the largest finite simple group. It's still finite, but the order is a few magnitude large. Yeah, very large. Right, so these are just finite for finite order one. So these are found. So you know how long is this proof? This proof actually take few years. And then there are like 5, 6, 7 books like that, just to prove all of these things. Okay, so actually it's a very long work, very hard work. And some of them try to group them together, such that it looks like a periodic table, chemistry periodic table here. So all the sporadic group live outside here, cannot classify. These are no chemistry, these are finite simple group. Yeah, let's see where's the monster. Can I see the monster or not? Let's see where's the monster. I need to show you how big is it. Is this guy monster or not? Yeah, I think this is monster. This is how big it is. Okay. Yeah. Actually, you can go YouTube. Find by 3 blue 1 brown. 3 blue 1 brown. Okay, monster group. A very nice introduction to monster. Okay, 3 blue 1 brown. Okay, 3 blue 1 brown. You can look at it. Monster group. Very interesting. Yeah. This is the last one to find. Turns out that this has something to do with something called leash lattice. Okay, and then this leash, is it leash? I think it's leash. And then it's a E8 lattice, and then this lattice here actually has some role in string theory. It has some role in string theory. OK， 有问题吗？其实我们可以提早。哎，没有，不要放先拿名字先，先拿名字，然后你们想问题，看看有问题问嘛。可以问一下这些 group property 好像曾子涵有在吗？ 子涵有在吗？曾子涵，好久不在了，好像。金鱼，金鱼 OK，子豪有，戴奕晨有是不是？OK，金鱼，邱腾在，冰夏没有啊？冰夏，小月，哎，小月，你朋友呢？没来，还有你是 OK，子涵有，孙佳怡吗？你朋友？OK，好，方宇在，方宇有在吗？OK，在。王佳怡呢？他呢？也有事，不知道。OK，朱瑶有，林夕有，凡，钟一凡呢？没在。康平、若星、早色、演出、昊天、金星、你好、金泽、瑞秋、金鹏呢？Okay. Okay, so all right. So when we upload the typeset note, right, there's two versions. One is a current lecture note, the other is a preliminary knowledge. So when you read both document, if you found there's something lacking, okay, you let us know. Okay, we will try to add enough so that you can how to say perform in this class. Any knowledge that you need in this class, we will put into this lecture. Okay, no. So if you found out that hey, this part I don't understand, or you think that hey, this part we should add it in, you tell us. Okay, we will do it. Okay, no. Does it make sense? Okay, we try to give you the latest version, I think, by today or not tomorrow. Okay, so that you can do revision for Thursday. Okay, so that you can do revision for Thursday. Right, so class dismissed. Okay, see you on tomorrow. 我感觉还有很多，但是也没有时间，我们先这样。要不要认真对待一下你的课件？我觉得要小心。啊？不用证明。我只是觉得你给的你要我们给的 exercise 太多了而已。哪一个？我只是觉得你写了一堆 exercise solution，但是我觉得有些 solution 根本没有必要写，有点给他们动脑子的